Gokul Reddy, are you able to hear me? Reply the chat box. Okay, okay. Just I'm checking the audio.
Okay, ma'am.
Dijo, good morning. Lijo, are you there? Belvin Lijo.
இருக்கு மேம்.
Today you are going to start the session or Vinod sir is going to start?
சார் வருவாங்க மேம்.
சார் ஸ்டார்ட் பண்ணுவாங்க. சரிப்பா, ஓகே. Good morning, students. We'll start the session in another 5 minutes. Vinod sir, good morning.
Morning, ma'am.
Sir, we'll start in another 5 minutes.
Yeah, sure, ma'am. Ma'am, make it a co-host and Lijo.
Lijo also, okay, sir. So, good morning, students. Today also the resource person is Mr. Vinod sir from Wilma Communication. He will be continuing with the microstrip antenna design. And he will be assisted by Belvin Lijo, who is the alumni of Satyabama. He is 2021 passed out student. I welcome you both, Vinod sir and Belvin Lijo. Sir, you can start.
Yeah.
I'm handing over the session to you.
Yeah, sure, ma'am. Thank you, ma'am. So very good morning to one and all presents here. Yesterday we draw one simple patch antenna. Due to some technical error, we can't continue that one. So today we are doing the same design once again and verify all the results. So after completing this one, we discuss about the solver operations and what are the solvers is there and what is the effective of that solvers. So everything we analyze today. Okay. So initial condition yesterday itself we are knowing. So we are having a three differential windows. So one is in a design window, another one is in a property window, and third is in a project manager window. So the project manager window means the entire project information, so like results, feeding methods, what are the techniques we are involved, and what is the optimistic technique, everything is having in that window itself. Okay. And the second property window having the entire details about the particular designs. So that is a second window, and third window is in a designer window. So this designer window is a purely a three-dimensional window. One special case of this software means the software's entire process is done in 3D models. And other than that, Comsol and Magus only are having the another 3D softwares, and balance softwares, all the things are on a 2D analyze alone. So now today we are also doing the same design. So same, we don't modify the things. So the first case, we are selecting a substrate method. So substrate is a three-dimensional factor. So we had to select the three-dimensional box here. Okay. So we draw one three-dimensional box. So first the three-dimensional box, all the three-dimensional elements comes in the terms of solid, and two-dimensional elements means that is called like a sheets. In the left side, you see like a property window. It's produces solids model, and under is in a solids. That solid, now we are draw one box. So this box they are converted into a particular materialistic characteristic. So we double click on that box. One means we have one modular window. This window we change the name as in a box 1 into as in a substrate, and we have to select a material process. So material means a lot of materials is there. Yesterday itself we are analyzed that one. The same things as here you have to enter into the library, HFSS library, high frequency synthesized simulator library means that library is connect around 300 material characteristics, and you select your what type of materials you want. You have to select directly. Here I have to select retardant fourth order substrate. So I have to choose a for epoxy. So okay. So this is the first case. The first step of design process is to do a substrate, placing a substrate. So now we are placing the substrate. Okay. So now we converted into that box into a substrate, and below the substrate we are having a create box option. You double click on the create box means you got a one modular window. So this window is called like a property of that box. Property of that box. So this box contains position and dimension of the particular substrate. So position means from 2D we have to take a 2D. So 2D means is an XY plot. So XY plot means what is the originated value? Always is an 0. So three-dimensional also as an originated value, having an originated value. That originated value also 0, 0, 0. So you just enter into the position 0, 0, 0. And next one x. X is the length of the substrate. It's not like a length of the radiating layer. Length of the substrate. Its formula is LG is equal to L plus 6H. We need to follow this formula. So you got a approximate got an exact value of 21 mm. So just a 0.2 meter. Okay, 0.2 meter. So 21 mm. And next thing is y. So y is the width of the patch. So width of the patch here is in a square patch. So square patch means length and width both are is an equivalent one. So again you have to select same 21. Next thickness. how much of thickness it's having. This formula is having h equal to 0.0606 lambda divided by root epsilon r. Here, the term epsilon r provides a permittivity of the particular material. That means current carrying capacity of the particular dielectric material is called like a permittivity, relative permittivity, that is denoted in the terms of epsilon r. So that's why we are putting putting that 4.4 in that formula, means exactly we got 0.158 approximately, sorry, 1.58. So approximately I take a 1.6 mm. Okay, so 1.6 mm. That's all. Give a apply and okay. So that is an expandable case. So you give a fit window, means the all more overall structure is comes into our item process. Okay, so this is the substrate box. So three-dimensional box. This box having eight different phases. Sorry, six different phases. Okay, so each phase having some equivalent power supply value. Okay, next we need to make a copper sheet. That means layer of copper. So we quoted the copper. So copper means this is a sheet. It's under comes under in the terms of sheet. So we select a 2D materials. So in the 2D material, you select one rectangle. So just to select and draw one rectangle. So it comes under in the terms of sheet. You just verify that property window. It's having the sheet. Okay. So double click on that rectangle one, means on modular window produced. You just change the name. So name is ground, and also we change the color. So because we need to analyze the separate different colors, so I had to select some colors. No, just select a red color. Yes, just okay. Apply and okay. Okay, next we enter into that create rectangle option. So create rectangle means this is also a positionated window. Ground and substrate both are always is an originated. So 0, 0, 0. Okay, here that first 0 is indicated x position. Y that second 0 indicated the x position and y position, and third one is in a thickness. Which place you have to place, either as a ground. So ground means it's origin, and top radiating layer means it's a 1.6 mm thickness. So you just modified that thickness. That's why you need to enter into the third one is different cases. Okay, and next x is y 21 and y also is 21. Just apply and okay. So now we enter into we assign that particular layer into a conducting layer. So right click on that ground, enter into assign boundary condition. You select perfect E. Perfect E means perfect electrical conductor. So perfect electrical conductor means it is called like a copper. So now we assign that ground layer. That means a ground coating layer is in a perfect copper conductor. That's all. So now you just select that ground and verify that ground. So this is a ground. Okay. In top radiating layer is an empty, and bottom only we are placing ground. Okay. Next, we enter into another one, create one rectangle, another one sheet, because we need a copper coating layer in the top radiating layer. Okay. So we saw one we draw one rectangle layer. Then we enter into the create rectangle option. Just so modify that rectangle one into name as a patch. It's a radiating layer. It's called like a patch. Okay. So you just modify that values. So check the colors, green, select a green color. Yes. Okay. Okay. Then again enter into create rectangle. From this one, this is the this formula is L is equal to L effective plus L effective minus 2 into the 2 into del L. So that is a length value formula, and width value formula is lambda by 2 into root of epsilon r plus 2 divided by epsilon r plus 1. That is the W formula. So based on that formula, you got the length and width value. From that length and width value is length 11.45. That is the exact value. But we need to place the position first. Okay. So we need to make that one into a middle. So you need to find the middle value. So first x position. So we need to find the x position of that radiating layer, means that formula is LG minus L divided by 2. LG minus L divided by 2. That is the formula. So based on that formula, we got 4.8 value. That value is 4.8, as it is of same because it's a square. Okay, so same into y also. And third one is a thickness. So thickness value is 1.6 because we need to place that radiating layer into top of the material, not a bottom. Bottom means it's a 0, top is 1.6. So enter into 1.6. And next x value is 11.45 and y value is also 11.45. That's it. So just give an play. Okay. So we have to place the exact mid of the total material. The radiating layer is exactly placed in the mid of the total radiating layer. Next, we need to assign feed line. Okay, so feed line. So feed line means the formula is length of the feed line is lambda g by 4 and the width of the feed line is barrier condition. That means b is equal to 4 pi divided by 180 into root of 2 divided by epsilon r or epsilon r into epsilon r effective plus 1. So that is the barrier condition formula. Based on that formula, you need to find the width of the patch here. So that operating that feed line length is, we got 8.5. Length is 8.5 and then feed line width is 1.6. As per the calculations, again we draw on rectangle. So we need to modify that rectangle into feed line and we enter into create rectangle option. So we enter into the create rectangle. So that create rectangle, the first thing is feed line position. So x position is LG divided by 2 minus WF divided by 2. LG by 2 minus WF divided by 2. So LG is 21 divided by 2 minus WF 1.6 divided by 2 means exactly we got 8.9 is the first position value. 9.7 is the first position value, and in x-axis y value is always 0, right? That's why we have to place the value in the x-axis. So 0 comma, you have to place that feed line into, that means that resistive line into top radiating layer. So that value is 1.6. So this is the position. And next x is 1.6, that is a thickness of the width of the feed line is a 1.6 and length is 8.5. So just apply and okay. So now we saw that blue and green. Green is the radiating layer, blue is the resistive part of the material, that means feed line. Okay, both are is not an interconnect one. So we need to make an interconnect. So we need to make an interconnect means additionally we put one capacitive effect in that radiating layer, means then only it's make a perfect conductor. So again we put on slot. So again you have to select on rectangle. So we need to find the position of that inserting path position. We need to find the inserting path position means the same thing, LG divided by 2 minus slot width divided by 2. So LG minus 2 minus slot width divided by 2 means the exact slot position is 8.9. Slot position, that means create rectangle slot position. The first position value is 8.9 and second one is a 4.8, because above the 4.8 only we need to place a slot. So 4.8 comma 1.6. So that is the position value, and width of the slot is 3.2 and length of the slot is 3.7. What is the length? Why we select the length is 3.7 means more total feed length value is 8.5. That feed value is excess value is above 4.8 only. So 8.5 minus 4.8 means you got 3.7. So that is our feed length value. So just apply and okay. So now we make it another one rectangle to use the interconnecting process. So first select the patch and select the ground also. Plus control and select the ground. Sorry, slot, patch and slot, and right click. Go for edit, and in the edit we have a Boolean operation. You select a Boolean operation. In that Boolean operation having subtract. So select a subtract. So that a blank part means which one is the originated part, and tool part is which one is the subtraction part. So blank part means originated and subtraction part is tool part. So in patch is in a blank parts, and a slot is the tool part. So select OK. That's it. So now we merge, we cut that particular place in that radiating layer. So the feed is directly interconnect with radiating layer. So now we need to make the impedance matching characteristics. So we select a patch, control, and feed line. Same, right click on it, go for edit, and Boolean, you select unite option. So now unite option, now the total patch is united. So it is produced like a single element access method. Okay. So next we right click on the patch, go for assign boundary. So that radiating layer also we need to assign perfect electrical conductor option. So you have to select the perfect E. Just okay. That's it. So now the entire antenna is ready. Now we assign a port and give a power means the antenna will ready to run. Okay. So we need to place the port. Always the port is start edge of that radiating. That means feed line. So that point is called like a port. Okay. So we need to make a port. So before going to place the port, you need to change the axis. Okay. Because the port is lying in that XZ axis. So you have to select that axis into XZ. Okay. So we rotate the patch for that XZ and draw one rectangle. Change that rectangle one name into port. Give a different color because we need to verify the variety of colors. That's why. Okay. And again, go for create rectangle. From this rectangle, in our power insert line is parallel to y-axis. So that axis is y. So we have a correct position. So we enter into that same feed line position. So what is the feed line position here? 9.7, comma 0, comma. This port is starts from 0 to 1.6. So here that y is that position also 0. Next, x value is width of the port. So width of the port is equal to width of the feed line. So 1.6, same 1.6. And then z is a thickness, right? So thickness, what is the thickness value here? Same 1.6. So again, we apply 1.6. Just apply and OK. So now we place exact port position, right? So this is the exact port position. So we need to assign the power line. Okay. So select that port, right click on it, go for assign excitation to select a lumped port. We have 3 different port: circuit port and focal port and lumped port. And wave port also is there. We want to analyze the incident wave characteristics. That is also possible. And we need to link it with another one field characteristics means. That means they need to place this antenna into some particular application field means that verification also it's possible one here. Okay, that means live demo 3D also it's a possible one. But now we are doing only for antenna application simulation only. So we select a lumped port here. So lumped, what is the lumped elements? The same three elements. That is the or LC is called like a lumped elements. So we select the lumped port. So change the name one into port. Port. That's it. Port of S11 or whatever it's. You can do anything else. I'll select a port only and a full port impedance. Just note it down. Full port impedance of the any of circuit is called like a 50 ohm, and half port means it's a 72 ohm, and quarter means it's a 108 ohm. So this is the nature progress of the port impedance value. So now we need a in antenna always analyze in the full port impedance. So I had to select the 50 ohm. Just next. That next we have an integration, and because power we need to integrate the power from ground source to ground. Okay. So select that none. Select a none means you have a new line option. Just click that new line and place the bottom of that port and draw one power line. Okay. So we define that integration line. So next and give a OK. That's all. Finish. Okay. So now we have to check with the project manager window. In the project manager window, we have a boundary condition. First, we have to select the boundary condition. So in that boundary, we need to give a two perfect electrical conductor. One is a ground. So you just select a perfect E1 means ground. Ground also having the perfect electric conductor value. And next perfect E is in a radiating layer value. So radiating layer also perfect conductor. And next excitation, we need to check the excitation, whether the excitation is correctly placed. Yes, it's a correctly placed. Now the total antenna is ready for running conditions. And before going to running conditions, we need to check if you want to analyze the antenna into a real-time process means we need an air medium, right? In that software, we can't make an air compressing method. So that is also having one formation. So that formation is called like a lambda g by 4. So all the values is in a minus of lambda g by 4, lambda g by 4, lambda g by 4, all the position. And then you have to take a grounded separation values, or otherwise you just right click on that design, just right click and go for create open region. Just click a create open region. So you got something else. So you have to enter into the operating frequency. Here our operating frequency is 5.9 gigahertz. So you select 5.9. So just okay, that's all. So it's automatically produced the operating region box. So this box is contained the air box. The antenna is placed in the mid of that box. So equal circle, that means we need a circumference path. So that's why we had to take a operating course. Okay. So now the total antenna is ready for running. So before going to run, we need to check whether we miss any of condition or not. So going to simulation, you just select the simulation and verify the validation factor. Validation factor. So that analysis setup is missing because we just give a port line only, but we don't fix that analysis, which type of analysis we want, either a Fourier transformers or inverse Fourier transformer or fast Fourier transformer or Z transformations, which type of analysis we want. So we didn't enter here. So again, so just close it and go for model, select a model, or else as okay, go for setup. In that setup, you select advanced. So in that advanced means we have a different set of values. So again, you just enter into our your solution frequency. What is our solution frequency? It's a 5.1, and you just enter into the maximum number of passes. What is a passes here? That passes is called like a number of iteration at value. So that iteration is you just give a maximum value means you get a particular the most accurate value. So here I have to select a 21. 21 is the common base value. After that is a 42 and then 108. So this is the passes value. So here I have to select a 21. Just okay. That's it. So next we need to change the sweep type. Sweep type means which type of analysis we want. We have a two different types of analysis: fast Fourier transformation, inverse Fourier transformations, and interpolating and discrete Fourier transformations. Here we need to select a fast Fourier transformation. So fast. Next, you need to check the start value to end value. So this is the axis value. Which axis you want? So I had to select a total value. Okay. So 1 to 7 or 1 to 10, whatever it's. I had to analyze the 1 to 10. 1 to 10. And the distribution having a two part. One is a linear count, and then another one is a linear step. Step means it's a pulse response. Count means it's a point response. Both are as in a difference, but at present we have to select the count value. So count value is always a fixed value, is a 4.1. So you don't need to modify. Just okay. That's all. So again, we just validate the design. So now all the green lines will having. So our validation is perfectly matched. So just close this window and save this project into some particular location. What is you want any location and what is the name? So you have to select the everything. So I'll just give a project file. Okay. That's all. So now we need to go to analyze process. Go for analyzed. Yes. Just show the message and progress window. Message window also. Message. Yes. So in that bottom, you have some green line moving, right? So this is the process running. And before going to see the results, we need to we need to what is it how the software is working. So we need to analyze, sorry, we need to study of this first. Okay. First thing, I think you are all study in signals and systems, right? The signals the system, fast Fourier transformation and inverse Fourier transformation, discrete Fourier transformations, you all studied. So what is the process here? Process there? You just, if you give a one polynomial sequence means you have to select the order of the sequence and modify the sequence into that solution frequency used on matrix formation. Same thing here also, and get some numerical fast Fourier transformation sequence. So make that sequence into a DSP process analysis. So from the DSP process analysis means it is called like a butterfly wing diagram solution progress. So you need to analyze all the things into n power value. So n power, first of all, we initially give n equal to 0 and n equal to 1 and n equal to 2. So you need to provide some wing structure. After that, we got a one solution sequence. Okay, so make that solution sequence into the matrix formation. So y is equal to mx plus c constant value. So after that, we get the y matrix value. Then that y matrix, you need to provide upper triangle 0 and lower triangle 0 option. And that mid of the corner is a corner only is the output sequence of the some particular problem, right? So the same process, same analysis method only here also, that running process, that exact that means that the triangle value is called like a output frequency of that particular material. Now the analysis is completed, so we enter into a result part. So the project manager having results options. So you just select the results and right click on the result and go for create model solution data report. From that one, you have to select a rectangular plot. So you just select a rectangular plot, and we need to check that S parameter. So here we have a S parameter, and then the output quantity is in a port. So always loss is what is the loss function value? What is the that means unit value of that function means a loss means it is the dB. So you just select the dB and give a new report. So new report, our exact frequency is a 5.9 gigahertz frequency. You just mark it. Now we got a 5.95975 gigahertz. Just 0.07 is it's a negligible condition. That is not a matter, but we got a 5.9 exact resonance. Okay, then again you right click. You need to place some strip lines, because all that reference antenna point is a 10 dB is the reference antenna point. That means that the initial condition of that antenna is in a dipole antenna. The dipole antenna loss is minus 10 dB. So below minus 10 dB value only we have to climb like a low profile antenna or low loss antenna. So you just marginated one axis means you got some value. So this is we have a minus 30 dB of loss. So the loss is maximally minimized one, and that our application frequencies of 5.85 gigahertz to 6.11 gigahertz. So yesterday we saw exact V2X communication application. That means vehicle to anything application process. So this antenna is perfectly matched for V2X communications, because we don't have any harmonics from left side and right side also, that particular exact position, right? So next we need to go for coefficient value. So this is RL value. So reflection coefficient means tau is equal to 10 power minus RL divided by 20. So used on that formula means you have a tau value. So after that we need to find the VSWR. So VSWR is equal to 1 plus tau modulus of 1 plus tau divided by 1 minus tau means you got that exact VSWR value. The same exact VSWR value also provide in that Simulink path. So you just select the result, right click on that and go for create model report. In that model report, you have a rectangular part. You just select the rectangular part and select a VSWR. Category is in a VSWR. VSWR is a constant value, so there is no unit. So just give a new report. That's it. So you mark, you right click, make a right click, select a marker, just place your exact frequency. So our exact frequency is of 5.95 gigahertz. We got around 1.0585. The theoretical value of the VSWR is 0 to 1, but in a practical condition, it is a 0 to 3. Yesterday itself, we discussed about that one. The same thing here, we achieve 1.058. So 1.058 means it's merely equal to 1. So here we satisfy the theoretical condition also. So before we give one formula, right? VSW is equal to modulus of 1 plus tau divided by 1 minus tau means you just calculated that things means you got the same value. So this is one of the proof for theoretically this antenna is correct and practical as well as this antenna is correct. Okay. Next, we enter into the power pattern. So power pattern means we need to analyze the gain. Okay, overall gain of that running antenna condition. You just select the results, right click on the results, go for create far field report. Antenna having a two field, one is a near field and another one is a far field. Always antenna's near field is a 0, but in a 5G antenna and then more than a 5G fifth generation means that that antennas purely depend upon near field alone. It's not like a far end because it is a very low short wavelength values. So that's why. But here we need to check the far end value because this application is purely based on autonomous cars. So autonomous cars means in the far end direction we need. So we just select the far field report and go for 3D rectangular plot. Select a 3D rectangular plot. Sorry, 3D polar plot. I'm sorry. Results, right click on it, go for far field report, select 3D polar plot. So we need to select a solution is in a primary sweep because at present we have a sweep type. So you just select a sweep and select the categories in a gain and output that quantity of that gain is a total gain we need, and then gain unit also is in a dB. So you select a dB and give a new report because we need a total gain. So that's why we give a new report. So here we got that minus 7.4 dB as a gain. So it's a purely negative gain. So we need to modify this gain into positive. So that term is called like a optimization technique. So we need to modify this gain also as in a positive, right? So go for design. From that design, the ground you just make a square hole in the middle of the ground. So if make a one square hole in the middle of the ground means it is provide a reoriginated source. So it is used to increase the gain value. So you just make another one rectangle, you draw another one rectangle and go for create rectangle. Create rectangle. You need to check the middle value. Here I have to take a 2 mm cross 2 mm square. So this is the nature of that value is lambda g by 16. So I have to take a lambda g by 16. So it is 2.1 something. So approximately I have to take a 2. So we need to find the mid value is 9.5, 9.5, 0. 9.5, 9.5, 0. X value 2, Y value also 2. So just apply and OK. And select the ground and select a slot. Right click, go for edit, Boolean and subtract. Just give OK. That's it. So now this is the ground. In the ground, we insert one capacitor. Okay. So the slot is called like a capacitor. So just go for again simulation, analyze all. In a ground slot doesn't affect with the return loss. So that is not a problem. So it's take us some time because in the ground we just make a deflected, right? So it's take a little bit of time. There are a lot of simulation software is there. This is an ANSYS electromagnetic inductive solution, and the next one is a CST, compact systematic analysis, simulative analysis, and third one is a MATLAB. I think you all know about that MATLAB, and then ADS, and next one is an IIIrd, integrated electromagnetic three-dimensional structure, and then fifth one is CAMSOL, and then seventh one is Magus, and eighth one is EM Pro, and then what is another one is called like a Priyank. So we have 9 different types of softwares. Compared to this, all the softwares, exact 100% effective applications, effective results, which gives like a Magus. Antenna Magus, it's provide a 100% solution frequency for both simulation as well as real-time fabrications. Both it's get us the exact value. That means 100% perfectly matched one. And next second of that one is ANSYS HFSS. It is provide like a 99.9% of efficiency, 99.9% of efficiency. And third one is antenna ADS. That means ADS. It is called like a ADS, analog divisional structure simulator. So that is called like a 97%. And fourth one is a CST. Now it is provide a 94.5% of efficiency for a real-time process. Because if you do one antenna into simulation process, but some changes will occur in that real-time process. Why it is occur means the real-time object is fabricated by man-made object or else in a computerized systems only, and also environmental also having some little bit of losses. Environmental losses also is possible to occur in that particular board. So it is give us some little bit of different cases. Okay, so now we got the gain value. The 3D gain plot value is 4.7 dB positive gain. Just we put a one mid hole. In before we have a minus 7.4. Okay, and now we just put a one mid hole only. So just show the design. Select the ground. So just to put a one mid of the hole only. So if you place one mid hole means gain will be increased one. So this is a general concept. Because in our one perfect running circuit, you just add a one capacitive effect means that capacitive effect is used for capacitive means it's store and reforward. So store and reforward means it has give us some boosting technique is there. So some boosting technique occur means highly the transmission will go for the transmission speed is increased. Automatically it increase, so automatically the gain value is increased. So same formula only here also we implement. So we got the value of the gain is 4.7, and we need to go for analysis of directivity also the same thing. So directivity is a constant value, but here we need to check the dB value only because it's possible to get a dB value. So if you select the same process, the results, right click on it and create far field report and go for a 3D polar plot. In the 3D polar plot, you select the directivity and select the unit function value is in a dB means you got a directivity value. So just select the double click on the directivity. So directivity is a 6.2. So we need to find the efficiency of that particular antenna. What is the efficiency factor? So yesterday itself we discussed gain is directly proportional to directivity. We remove the directional constant means we introduce some constant notation value. So here we enter into the neta is the constant value. So G is equal to neta into directivity. That means gain is equal to neta into directivity. So neta is equal to gain divided by directivity into 100%. So that is the form factor value. Here our gain value is 4.7 divided by 6.2 into 100% means it exactly got a 72 point something percentage. But in a microstrip patch antenna, 58 to 60% above is an acceptable case. Okay, so it has got a 72% efficiency. So this antenna is perfectly matched for V2X application. And next thing, we need to analyze the pattern, radiation pattern, how the power will radiate in that surrounding. So we need to check that condition. We have two different conditions. What is the two different condition means? Two perfection angle is there. One is antenna always having a two angles. One is alpha and another one is an theta. So alpha and beta. So alpha means it is an horizontal polarization value, and beta means it's a vertical polarization value. So go for results and right click on that results, select a create far field report. In that report we have a radiation pattern. So you just select the radiation pattern and select the primary sweep into last sweep into primary sweep, and go for you have to take any of things. That is not a problem. If you want to take a gain pattern means that is also a pattern, and real time electrical transmission value means it is notated in that RE value. So you just select the RE value. So from that RE value you have to select the RELHCP. That means right hand polarization process, because we have a two different polarization in a right side and left side. So right hand polarization and left hand polarization, both we need to analyze. So select the right hand polarization. That value also considered as a dB. So you select the dB function and then go for primary sweep value into pi. So pi means it's a beta. Pi value is an elevation angle. So you need to concentrate on elevation as in a 0, and theta is an azimuth. So azimuth means you just give a 90-degree, your input is processed in that 90 degrees. So in 90-degree means you just get the opposite direction as the main direction. So 90-degree opposite direction is called like a 0 or minus 90-degree. So now you have to select a 0. So theta value is a 0, and we select the perfect frequency. What is our exact frequency here? 5.975 gigahertz. So the same 0. Okay, 5.975 gigahertz. We just select the frequency. 725, right? Just give a new report. So theta, next value is theta is 90 degrees. Yes, add a trace. Change that on plus initial condition also. So red line, just make it a dark one. 8. So yesterday itself I told in a 5G antenna, 5G applications means we must want a circular polarization. So antenna outer ring having a red line, circle line. So circle line means that is the far end direction. So in that far end directions we got a circular polarization. In near end we have a little bit of loss, but exactly it's reflected with the 0-degree process. So main axis is in a 0 degree. So totally we got a positive progressing thing. So this is called like a so we need to make what is that PQRS analysis means it's a minus 30-degree to plus 30-degree as a process. So this value is contained around the 19 dB of process. So total directive pattern, that means wavelength, total direction wavelength gain value is 19.5 dB as an beam width of this antenna. So this beam width of this particular antenna is 19 dB, and that's it. So make the PQRS point means this is 13. And next 6 one is there, so you just add a 6 means it's a 90. So that's it. Okay, so this is the beam width of the antenna. Next, same value we have to take another one condition, RHCP. Okay, so go for create far field report, take a radiation pattern, and same thing. So if you tilt the angular antenna into main axis is in a minus 90 degree or plus 90 degree, minus 90 degree or plus 190 degree, both is in a same. That means LHCP is equal to RHCP. So that electrical field and magnetic field is perfectly matched. That means Fleming left hand rule and Fleming right hand rule, both are is an equal, means that is called like a reciprocity principle. That means in antenna 1 will generate the, it will give an input, means antenna 2 generate the EMF. That is the concept of that means reciprocity principle. The same principle only here we proved. So LHCP is equal to RHCP. So this antenna is perfectly matched for circular polarization, and also it is exactly worked in 5G application. So these are the results. So this kind of results only we need to analyze whether based on our theoretical, we need to check our results factors. That's it. So this is the entire results, and I think in that mid gap I'll just explain about a solver analysis process also. So solver analysis means first initially it's converted, the total structure is converted into some polynomial sequence. After that we assign that polynomial is an n value, n number of values, and after that we assign n is equal to 0 and n is equal to 1, n is equal to 2 based on that n order value. So we need to analyze, means we got our solution. So based on that solution is equal to y is equal to mx plus c. So based on that one, you just generate that one matrix. So 3 cross 3 matrix. Based on the 3 cross 3 matrix, you just provide, you just find the eigenvector. After that, you make a upper triangle 0 and lower triangle 0, means exactly we got the mid solution value. That mid solution value is now exact output frequency. This is the solver analysis process. So right now you just understand, if you want to design one antenna, means we need all the applications. We need a mathematicals, we need the signal system and transmission line, proper transmission lines and waveguides, and then DSP, and that application is purely depend upon wireless communication. So we need a 5 important subjects. All the 5 important subjects is integrated means then only we do one antenna. That's it. Okay. So is there any doubt? Is there, means you just ask now, are ready to give the story. Is there any doubt? If you have any doubts, means now you can ask.
Students, if you have any queries, you can ask sir, he'll clarify it. So the simulation tools comes in 5th unit, last topic. So I request all the students, all the participants to fill the form which I have posted in the chat box. Okay, Vinod sir, I think no queries.
Okay, ma'am. Just wait. I had to show the testing results only.
Okay, sir.
So this is the exact fabrication model of this antenna. I think all are visible my screen, right? So this is the exact. Ma'am, is my window is visible now?
Yes, sir.
Okay.
I can see that slide number 11.
Yeah. Okay, ma'am. So this is the exact fabricated model. So this model is tested under in our college VNA. So in our college we are having a VNA. So Satyabama having a VNA. So in that VNA we tested this this corresponding antenna. So this antenna is perfectly matched. So we have a differences around minus 10 dB gain, 10 dB of loss only is in the difference. So this difference is a natural case because an man-made fabrication. So it is possible to occur, but it's exact resonance. We got that exact resonance. So this is the real-time testing. So this antenna is perfectly matched for real-time applications. If you want to find the efficiency of the antenna, means simulation characteristics also having the efficiency characteristics. Otherwise, you need to get gain divided by directivity into 100%. So gain value and divided by directivity value into 100% means you got that exact percentage of the efficiency of that antenna. Okay. Any other question?
One student has raised the question. It is how can we find the efficiency of an antenna?
Yeah, ma'am. Now just
now you explained. Okay, sir.
Any other question, guys?
Any other questions, students?
Okay, if you want more details, means you contact me as a person. I'll just explain for everything. I'm having my details, so you just collect from me. Okay. Thank you, ma'am.
Okay, sir. Thank you for today's session. Thank you.
Yeah, thank you.
Thank you, Belvin Dija also.
Thank you, ma'am.
Thank you. Students, any doubt you have? Hope everyone have submitted assignment 2. So this microstrip antenna design comes in third unit. Third unit, you'll be studying about the theory part, and the 5th unit, you'll be studying about what are the antenna tools available, simulation tool available. We'll be studying in 5th unit. So 5th unit, last topic is this topic only. So it is there in YouTube also, how to design a microstrip antenna using HFSS. Those who are interested in doing final year project in antenna, you can contact me or Sukhdev sir, we will guide you. So I request all the students to submit the feedback and attendance form. Only 90 response so far I have received. Okay, 105 response I have received. By participant is 300. I want everyone to fill that attendance form. Those who are filling that attendance form only, attendance will be given.